Okay, let's address the issue of this omega zero. Remember, omega zero was essentially, what's the volume in phase space that corresponds to one microstate? In classical physics, every point in phase space corresponds to a different microstate, so omega zero is basically zero. But that basically doesn't make sense, it doesn't work. But quantum mechanics tells us what omega zero is. So let's look at the quantum mechanical ideal gas. Okay, for simplicity, let's just assume a cube. I have n non-interacting particles in this cube. The energy of this system will be the sum of the energies of each one of those particles. What is the wave function for these particles? For each one particle, just look at one particle in this box. Do you remember the wave function? Come on, particle in a box in quantum physics.
Square root of something and sinusoid wave function.
Sine function.
Oh, yeah.
Okay, so your friend likes the sine function. Sine kx times x, sine ky times y, sine kz times z. Energy of this particle, kx squared plus ky squared plus kz squared over 2m. Let me also add the h bar squared. This is the energy. And let's say that this is the origin. My cube has side lengths L. So already this sine function is 0 at x is equal to 0 or y is equal to 0 or z is equal to 0. I have infinite potential outside, so the wave function had to be 0 on the surface. And furthermore, L times x should be 0. Now sine of L times x should be equal to sine of L times y, sine of L times, sine of kx times L, sine of ky times L, sine of kz times L. This should also be 0. This is the other boundary, which tells me that kx, y, or z should be equal to some integer times L or times pi. These are the allowed values of pi of k, because if this is the case, k times L is an integer multiple of pi, and at integer multiples of pi, the sine function is 0. And also, these numbers can be 1, 2, 3, up to infinity. They cannot, taking nx to be minus 1 rather than 1 basically changes the sign of kx. If the sign of kx changes, you get the same state, same wave function with a different phase, but it's the same wave function. So these nx, ny, and az numbers, they can take only positive integers. As an exercise, also in quantum mechanics, you see this is called the fixed bound. This is the wave function of particle in a box with fixed boundary conditions. You can also use periodic boundary conditions. So if you use in these fixed boundary conditions, your particle cannot leave the box. In the periodic boundary conditions, basically, if one particle enters the box, one identical particle leaves the box. So the number of particles in the box doesn't change. So the physics shouldn't change. So repeat for periodic boundary conditions. If you like, you can also imagine this periodic boundary conditions for an infinite space, homogeneous, the properties of the gas is the same everywhere. You just look at a finite cubic volume V within this space. Nothing changes. Everything is in equilibrium. So you can just study this volume V. So if we go back, gamma of E will be basically, remember, gamma of E is the number of microstates, so this is the number of n x, n y, and z triplets remember, for each I have n particles. For each particle I have these triplets, nx, ny, and nz. This I just goes from 1 to n. That's the gamma of E, the number of states having energy less than E, will be just the number of these three numbers for each particle, such that sum over I of h bar squared pi squared over L squared nxi and yi plus nzi, each one of these squared, is less than or equal to E. You see, if I find 3 n integers such that if I sum their squares and multiply by h bar squared pi squared over L squared, if this is less than E, I have a new state in this gamma E. So I can also write this as number of, let me use a different symbol, mi. I goes from 1 up to 3n, such that sum over I of mi squared, I from 1 to 3n, is less than or equal to E times v to the 2/3 divided by h bar squared pi squared. By the way, I can already say one thing. Gamma of E, or in fact even omega of E, is a function of E times v to the power 2/3 and some function of n. It's not a separate function of E and V. It can only depend on E times v to the 2/3, because this is the definition. You see, E and V doesn't appear in this definition separately. They only appear in the combination E times v to the 2/3. This is exact, by the way.
No, these are for additive cases. These are for additive cases.
No, this is, I have an isolated system of n particles. That's the only thing I have. And of course, this already tells me that S is a function of E v to the 2/3. So, which already tells me that in an adiabatic process, E times v to the 2/3 is constant. So I didn't do much, but I already know one form of the adiabatic equation. Well, let's say that S is some function of E times v to the 2/3. I'm assuming n to be constant throughout this analysis, and I'm not changing n, so I will not be differentiating with respect to n, etc. Well, 1 over T is derivative of entropy with respect to E, which is just F prime, evaluate that E times v to the power 2/3 times v to the 2/3, whatever that F prime is, P over T, derivative of S with respect to V at constant E, which will be F prime E times V to the 2/3 times 2/3 times V to the power minus 1/3. I'm just using the chain rule. And E. I still don't know what F prime is, but I can just cancel F prime in these equations. If I just divide the second equation by the first equation, I will get P is equal to 2/3 E over V, or E is equal to 3 over 2 PV. I remember for the ideal gas, eventually we will get PV is equal to NKT, so E is equal to 3 over 2 NKT. But already, with just this much, I know that for the ideal gas, E should be equal to 3 over 2 PV. Let me ask you a question then. When we were discussing thermodynamics, just using the equation of motion, I said that the energy, derivative of energy with respect to volume was 0. But now I have E is equal to 3 over 2 PV. So derivative of energy with respect to volume doesn't seem to be 0. What's wrong with this reasoning? Any ideas? You see, when you are taking derivatives of thermodynamic quantities, you have to pay attention to what you are keeping fixed. Our earlier derivation was dE by dV at constant temperature was 0. So if I am changing V, but keeping the temperature constant, I have to change also P. So in this expression, P is a function of V. I have to pay attention to that, to what I am keeping constant. So here, dE by dV at constant temperature is 3 over 2 P, but there is another term, 3 over 2 V dP by dV at constant temperature. So this will still be 0. So just by looking at, oh, there's the V over here, its derivative with respect to V is whatever the coefficient is. If you do that, you will make mistakes. That's just a warning. So just pay attention to what you are keeping constant. It will tell you what other things you are not keeping constant. Like in this derivative with respect to V, I'm not keeping P constant. Okay, so let's continue. So I just looked at this definition of gamma of E. If you change that less than or equal to sign to just the equality sign, that gives you omega. So omega basically has the same property. And we already know that energy of this system will be given by 3 over 2 PV. Now let's continue. What is this number? Let's try to calculate that number. Okay, so again, I have, if you just look at these numbers, you can say that, okay, you can just show them in a 3n-dimensional space, each axis being corresponding to one of those integers. But I cannot plot the 3n-dimensional space. So I will just stick with a two-dimensional space. Let's say that this is n1, this is n2. Now, along these axes, I have integer coordinates. If I look at the intersections in this grid, all those points corresponds to two integers on that grid. Well, what is this equation? Well, that's an equation. In this two-dimensional case, it will be n1 squared plus n2 squared is less than or equal to, let me call this number r squared. This is the equation of a disk in 2 dimensions. So let's say that it is this disk Now, what I need to calculate is the number of points on these intersections, number of these points with integer coordinates that lie within this disk. I don't go to the negative numbers because already here I know that all these n's should be positive numbers. I don't have negative numbers. Well, if you go to repeat this exercise for periodic boundary conditions, remember that in that case, k will be just the wave vector. You will have plane waves that satisfy these periodic boundary conditions. Plane waves can go in one direction or the other direction. So nx will be positive, plus minus 1, plus minus 2, plus minus 3. So you have the negative numbers also. But the result will be the same, the final result. I mean, I do suggest you to carry out this exercise repeating for the periodic boundary conditions because the n's can now take different values. Still, the result will be the same. You will get some other places to correct for these factors of 2. You see, on one hand, nx can take, yeah, you will see that. Let me continue with this one. So what is this? Well, I can just now imagine unit squares around each one of these dots. Side length 1. Well, since each one of these dots are separated by 1 unit, if I just put squares of side length 1 centered on each one of those dots, they will, the boundaries will overlap. There won't be any area left outside these small squares. So basically these squares of unit squares will fill all this area. Well, there will be some problematic cases. Let's say if I have such a unit area, such a integer coordinate also, I have a point over here. If I consider the unit area, well, some of it just goes out. Some of it will be inside my disk. If I consider, I don't know, there will be some point over here, one point over here. You see, this area will not be counted. If I just count the dots, that area will be left out. Whereas if I count this point, there will be some area outside my disk. But remember, all these problematic cases are on the surface, not inside. In fact, one of the reasons why we are calculating this gamma E will be if you go and actually write a small program to count the number of points, omega E as a function of E will be it will be a very irregular function. At least for this, if you have two integers n1 and n2, you see I can imagine an arc over here. There's no point on that arc. Or if I make it a bit larger, there are 2 points, a bit larger, and again, no points on that surface, let's say. So omega e will be a very non-uniform function. But if I calculate gamma of e, okay, it will be a stepwise function. It will always increase. But I can calculate an approximation to that one. That is the one we are working with, actually. That's why we are calculating this, the total number of states having energy less than E. Okay, so if you go back to here, gamma E would be the integral of d3n of m, such that m squared is less than or equal to e v to the 2/3 divided by h bar squared pi squared. By m squared, just understand m1 squared plus m2 squared plus m3 squared, etc. Let me make a change of variables. Yes, I said that if you go back, this was our wave vector for one of those particles. Momentum of corresponding to that particle will be h bar k x y z, which will be h bar pi over L and x, y, and z. Remember those numbers m. You see what I am doing over here. So this is what gamma e is. I need to count these points with integer coordinates within this 3n dimensional space. Rather than counting them one by one, I just assign a unit cube to each one of those points. Now, these unit cubes, when I put them side by side, they will fill the 3n dimensional volume. So then the question is, what is the total volume of this region? We will find some number. Well, within that volume, I am just filling it with unit cubes with unit volume. So how many of them I can fit? Whatever the volume is. So if I calculate the volume, that will approximately give me the number of points with integer coordinates within that volume. That is what I am aiming at now. But still I need to calculate that volume. Well, I don't want to repeat the derivation that I did before using momentum and coordinates, so I will somehow try to convert this integral to my earlier integral over momentum. That is why I'm looking at how momentum and these numbers m are related. And this is basically the relation. So if I set m is equal to L over h bar pi p, I have gamma of E. Well, there's the d3n over here. So that will be L over h bar pi to the power 3n. This one. Then I have d3n p, I'm integrating over all p, subject to the condition that p squared, remember, m squared was this condition I can write as h bar squared pi squared over m squared L squared Okay, I made one mistake. Let me correct that mistake. You see the energy, this is just the wave vector squared. So there's a 2m over here, which I forgot before. This 2m. So let me just change this m to some other number. Let's say Li squared, there's 2m over here. There's 2m here. So this is L, this is L, there is 2m here. This is L squared. But that condition basically becomes P squared over 2m is less than E. Again, I repeat, this P squared over here is the sum of squares of all the components of all the 3n particles. You see, L to the 3n is just V to the n, which is 1 over h bar pi to the power 3n, d to the 3n q, d to the 3n p, because d3q, each one of them gives me a v. Or each one of those dq integrals, each component gives me the length of, side length of the cube. There is one thing that I have to take into account. Here, P is greater than 0. And P squared over 2m is less than E. This is what this integral is. Now, in the classical case, we had d to the 3n p cube, d to the 3n p with p squared over 2m less than E. But p could be positive or negative. There was no restriction on p being positive. It could be negative. Well, I can do the same thing over here. Rather than integrating each one of those p's from 0 to some value, or rather than integrating over only this 1/4 of this two-dimensional space, I can just complete it to a full circle, count everything in them, but I have to divide by 4, or 1 over 2 to the second power. Well, the same thing over here. This will be 1 over 2 pi h bar to the 3n. So this is divided by omega 0 n. Subject to the condition p squared over 2m is less than E, with no condition on p being positive. Each component of momentum can be positive or negative. That is why I will be double counting. So that is why I introduce a 1 over 2 for each p integral. But remember, this should be equal to, if we somehow recover the classical result, d3np, d3nq divided by omega 0 n, whatever omega 0 is for n particles. But now we see omega 0 n, which, by the way, we had defined along the way as omega 0 to the power n, should be 1 over 2 pi h bar to the power 3n. So omega 0 is 1 over 2 pi h bar cube. So for each momentum and coordinate pair, we introduce a factor of 1 over 2 pi h bar, which is, by the way, 1 over h cubed. Well, vaguely, we did expect this because you see, there's the uncertainty relationship, which tells us delta x times delta p for each coordinate and momentum. Delta x, delta p should be something of the order of h, the minimum possible value. That is the minimum you can localize a state. Of course, in this uncertainty relationships, you have all these factors of 2's and pi's, which we don't know which one we would obtain, but this derivation tells me that, at least in this ideal gas case, for each momentum coordinate pair, I should introduce a factor of 1 over h. Each state in classical phase space can only be localized to a volume in a phase space to 1 over h. Every point doesn't correspond to a state, but every volume of h to the power 3n corresponds to one particle, one state in 3n dimensional phase space. You can repeat also this for the harmonic oscillator, for example. You'll get exactly the same answer. Okay, any questions in this derivation? Well, you see, basically we are looking at the same problem from two different perspectives. On one hand, we use the classical physics, classical phase space. We counted the number of microstates as being something proportional to the surface area or the volume of allowed space in phase space. Or we looked at the same problem from a quantum mechanical perspective by just solving the non-interacting quantum mechanical system of 3n non-interacting particles, particle in a box. And then we just counted the microstates, and in fact, we just recovered the same expression in both cases. And this allowed us to identify what is the unit of volume corresponding to each different state in classical phase space. You see, since it depends on h bar, there's no way you can derive this from classical mechanics. Any questions? Now let's try to be more specific about what we mean by an ensemble. Again, let's look at a case, a very simple case, one-dimensional harmonic oscillator. It has a very simple phase space, two-dimensional phase space. If the energy is fixed, the allowed hypersurface in this phase space will be this one. This is the surface p squared over 2m plus 1 over 2m omega squared x squared is equal to E. Now, since I just have a single oscillator in one dimension, I cannot really do statistics with that. But let's see, let's imagine you are doing some kind of a measurement on an arbitrary system, in fact. Eventually, I will consider the case that I have infinitely many oscillators, then I can do some statistics. But let's just stick with one. Now, if I, let's say, measure the position of this particle at a given instant, I will, let's say, this is x, this is p, I will observe it to be here. At a later time, I will observe it to be here. Let's say that I have infinitely many such oscillators. And they're all initial conditions. They will all randomly, but they will be at, they're identical, but many, many oscillators. Since the initial conditions were random, if I watch all these oscillators, nothing will really change. If one of them moves from this point to this point, some other one will move from this point to this point. So if I look at the distribution of the microstates of these harmonic oscillators, if in some sense my system is in equilibrium, nothing should change. But let's say if you consider an oscillator at here, or let me just say that there will be different oscillators will be at different points. Along this ellipse. Now let's suppose that I want to calculate, I don't know, the average position of these oscillators. So how do I calculate that? The average position, x, will be x of t dt from 0 to some finite time t divided by t. This will be the average position. My claim is that this will be the same thing as where n is the number of copies and xi is the position of the ith oscillator. So here, I'm just looking at one oscillator. I'm just summing over all its position over a time. I will follow it. Its position will change. It will just oscillate back and forth. That's called the time average. Because if you consider a realistic measurement, every measurement takes some time. During that time, the microstate of your system will evolve over many different microstates. This is what's called the ensemble average. You see, in creating my ensemble, you can also imagine creating your ensemble as take your oscillator, give it equal time intervals. At each different time interval, you get a copy. You make a copy of your oscillator. Yes, at t equal to 0, let's say my oscillator is over here. At t equal to epsilon, my oscillator is here. At t is equal to 2 epsilon, my oscillator is here. At t equal to 3 epsilon, it's over here, etc. Rather than following one oscillator over time, just make the copies of the same oscillator at different times. That is your ensemble. But by construction, it's obvious that since every member of your ensemble corresponds to a different time of that single oscillator, time average and ensemble average will be the same. I'm basically talking about the same thing. If, of course, I can calculate all these possible points. Now, you see, I can write this sum over I 1 to n where rho is the density of members of the ensemble. In phase space. see, for example, here I just took a discrete sample of my oscillator. But if you choose your time intervals very short, and you just make many copies, not just over one period, but over infinitely many periods, you will see that in let's say in this very small range, there will be many copies. I can define some density of my ensemble states within that very small interval. And when I'm summing over I from 1 to n of xi, well, all of those copies within this very nearby interval, they will have the same coordinate. Rather than summing over all of them, the position of all of them one by one, I just calculate the position of one and multiply it by the total number of copies I have with that position, and sum over all positions. So this is what this corresponding between the summation over all copies one by one and this integration over the ensemble density. At this up to now, I didn't really do much. I just I started by imagining a simple system. I follow it through over time. I identify the microstates, at least in principle, I identify the microstates that it will be in at different times. I just make many copies of my system, each corresponding to my system at different times, let's say. And in that case, rather than following one copy over time, I can just take an average of whatever quantity I'm trying to calculate over this ensemble, which is just many copies of the same system. And then when I have this many copies of the same system, I can talk about the density of these copies in my phase space. So rather than taking an average over the copies one by one, I can define this average over the density of my ensemble in phase space. The next question I will ask is, what can be this density? Yes, up to this point, I didn't make any approximation. I just made some definitions. My next question will be, what can I say about this density? Can I calculate it without actually solving my system? So that will be for our Wednesday lecture.